Everyone, so in this particular video we're going to go over problem set 4, I believe, which was the image processing algorithm. So basically for this particular problem set there are 3 problems. One is versions of filter, this program is filter, and the other one is recover. Okay, so let's get started with the filter one. So the idea in filter is that you're given a bunch of images and you want to apply those image filters. So in image processing, say you want to convert everything to grayscale, there's an effect in every Photoshop program to convert a given image to, say, a grayscale, or convert it to sepia, or otherwise, or blur it, right? So that's the idea that we're going to try to simulate today through the C programming language. Okay, so yeah, here are the different image processing effects that they want you to actually implement in the C programming code, and they provide most of the code already. So let's just get set up real quick and make directory PSET4 and change into it. Okay, so I have my ID here, which has Tideman open, which I was explaining the last time. Let me close that and let me open a terminal here. Open terminal here, and here what I'm going to do is I'm going to make directory. What I'm going to do is I'm going to create PSET4. And I am actually going to create filter less. Okay, and while I'm at it, why not create filter more, and while I'm at it, why not create recover? Okay, so I created these things, and then what I'm going to do is I'm going to change directory in PSET4 and push D filter less. Okay, filter less. Okay, so now what I'm going to do is I'm going to follow these instructions to obtain the problem sets template, which is wget, which downloads the zip file. Right, so I'm going to do this, and followed by unzip and remove. So unzip it and remove. Okay, the filter .zip. Okay, so that's what I'm going to do. Okay. Okay, so that's done. So let us see. Okay, we have our filter folder there. So now what I'm going to do is I am going to change into filter and execute ls. Okay. Change into filter, execute ls. Okay, so as you can see here we have our 4 files. Okay, so what they want us to do is modify this file, which is helpers.c, I think. So let's open that. Okay, yeah, so basically helpers.c represents the different image filters that will be used in the course of this program, and they're asking us to implement these functions. So let's go ahead and implement them. The assumption before we jump into the code is that you've already read through the different what's it called, the prompt as well as the walkthrough. So that's my assumptions. So yeah, so if you haven't already done so, go ahead and please read the specifications as well as watch the walkthrough. It's super helpful. Okay, so let's get started and implement first. I think grayscale is the first one. Okay, so with grayscale, we want to, okay, let's scroll up a little further. Okay, so what we have to first understand is this entire image is represented by a 2-dimensional matrix called let's open that real quick. So filters and helpers.h. So this is this thing, and then bmp.h has the actual RGB triples. So what they want us to do is pretty much we are passed in a RGB triple of image height and width to represent the actual image, and we want to apply some filters on them. Okay, and we already know the height and width of the image, so we can go ahead and apply it. Okay, so in the first one, it's pretty straightforward. What we want to do is they clearly say in the grayscale we have to take the average of the 3 values here, which is the red, green, blue values, right? So to convert a pixel to grayscale, we just need to make sure the RGB values are the same value, right? Blah 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 blah. In fact, somewhere they say here you have to take the average. I think it's in the walkthrough or here, but yeah, let's go ahead and do that. So we just have to take the average of the red, green, and blue values, and here, yeah. So we can take the average of red, green, blue values. Okay, and that should result in the final image. Okay, so let's go ahead and do that here. So what I'm going to do here is, so this is a 2-dimensional array, so all I have to do is just loop over this and convert each pixel here into the corresponding what do you call it, the converted grayscale pixel. Okay, So I'm going to go ahead and loop through this. So I have int I equals 0, I is less than height, I plus plus. And for int I is j equals 0, j is less than width, j plus plus, iterate over the width also. And what I'm going to do here is I have to take the average, right? So how am I going to take the average? Okay, I have to basically first get the RGB values for each one of them, and I can get that using in bmp.h, this structure's RGB triple, right? So RGB triple dot RGBT blue, RGBT green, RGBT red will give me the individual values. So what I'm going to do is, if I go back here and I say RGB triple current value equals image at ij, that will give me my current pixel. I'll call it pixel, it's easier to read. Then all I have to do now is I want to find what the final average is. So I say something along the lines of int average is equal to pixel dot RGBT blue, RGBT what's it called, blue, green, red. So let me go ahead and copy paste that, plus pixel dot RGBT red plus pixel dot RGBT blue RGB, right, green. Okay, and I go ahead and divide that by 3.0, right, and I round it. Okay, I believe that's all I have to do. And since round is defined in math.h, I go ahead and import math.h here. Okay, so now I calculate the average here. So what should I do after I find the average? I should assign the current pixel. So image at ij dot RGBT red should be equal to the average, right? And then image at ij.rgbt blue should be equal to the average, and image ij's RGBT green should be equal to the average, right? So I can sort of condense that and write on the same line like this. So image at RGBT green equals image at RGBT blue is equal to the average. Okay, and that's pretty much it. So all we're really doing is we're taking the current pixel, we're calculating the average of the current pixel, and we are assigning the image at ij to be equal to the average, right? And that's all we're doing. Okay, so let's actually run this and see what happens. Okay, so I go here, I clear this out, and let me run it actually. So I say filter this guy right here. I think even before that, to make filter. Yeah, so make filter. Okay, so that compiles, so that's fine. Filter G, this for grayscale. So I'll go ahead and do this. Okay, so there's the image created here. Okay, so it is indeed grayscale, as you can see here. Okay, so this works. Okay, actually we can go ahead and let us actually run the checker right now and see if the grayscale test pass. Okay, so okay, we're not gone to sepia yet, right? But grayscale successfully passes all test cases. So now let's move on to sepia and code that up. Okay, so for sepia, the idea is same, but instead of taking the average, we apply some sort of function that they give us. Okay, and this is a function that they give us. So let's copy paste this and paste this as a function, right? So actually, even before we do that, we have to apply this to each individual pixel. So let me go ahead and do that first. I equals 0, I is less than height, I plus plus. And then j is equal to 0, j is less than width, and then j plus plus. So I'm iterating over my two-dimensional matrix here, and I'm going to get the current pixel like I did here. So RGB triple pixel equals image at ij, so my current pixel. And what do I have to do here? So I have to apply those formulas, that they give us to the pixel. Okay, so we want to store this in some variable here. So the result of this will actually be may not be an integer, but each value could be rounded to a new integer, right? So let's go ahead and actually do that. Okay, so what I'm going to do here is I'm actually going to initialize them okay, so I need original red, original green, and original blue. So I'm going to say something like, let me see here. So I'm going to say int original red is equal to pixel at, let me do float instead. Float original red equals pixel dot RGBT red, right? So, or else let me just copy paste this here. Boom, boom, boom. For green, it'll be like so, and blue will be like so. Okay, so after I do this particular transformations, what I have to do now is the sepia red will have some value, right? Sepia green will have some value, sepia blue will have some value. So what I'll do here is I'll say pixel dot actually image at ij. So now I've applied the transformation. Now just assign those in the individual red, green, and blue. So RGBT red equals something, RGB blue equals something, and then RGBT green equals something. So let me go ahead and do that. So RGBT green, and then RGBT blue. Okay. So now I've applied this transformation. Now just set it. So if I just do something like this, right, this is not entirely correct. The reason being that these values may exceed 255 and we'll be assigning it to a byte, right? So we don't want to do that. So even though this is logically correct, these may exceed. That's what they say here. So they say that, of course, the result of each of these formulas may not be integer, but each value should be rounded to an integer. It's also possible that it's greater than 255, right? So what we do is we do a small check here. So we say if it's greater than 255, then make the ceiling as 255. So I'll just apply a quick ternary operator here. Else it will be the, actually let me just do int here and round these up as they say it, right? So round of this, round of that, and round of this guy right here, okay? So I'll do like so, okay? And I'm just gonna right now, so if it's greater than 255, I'll cap it or max it at 255, else I'm gonna assign sepia red, okay? I'm gonna do the same exact thing here, but it's just gonna be, if it's greater than 255, it's gonna be sepia green, right? And here, if it's greater than 255, it's gonna be sepia blue. Okay, and that's all I have to do. I pretty much apply transformations, and if it's greater than 255, I just assign, I just cap it at 255, also assign it as sepia red. Okay, so now it's going to go through each pixel, compute the transformation and the result value, and assign it correspondingly without exceeding the max. Okay, so let's go ahead and test this out with our program. So let me clear it, make. Okay, so it's saying, what is it saying? Undeclared RGBT green. Okay. Oh yeah, so it should be pixel.rgbt green, etc. right? Pixel dot. Okay, so now we're in good shape, I would believe. So let's go ahead and check that. Okay, so this looks good. For sepia, I believe we have to run .s here. So let's do that real quick. Okay, so now open this. Okay, that looks like sepia. Can't actually, sorry. Okay, now it looks like sepia. Okay, for a moment there I was just like, what is going on? Okay, so now let's run the checker now. And the test cases for sepia should pass. And while that's going on, let me introduce you to the next one. Next one is a little tricky. It's called reflection. So with reflection, you just want to reflect from right to left and left to right. So it should just be a reflection in the horizontal direction. So in this example here, if this is 1, 2, 3, 4, the first row would actually get flipped and you would have 4, 3, 2, 1. Similarly, if it was 5, 6, 7, 8, in the next row, it would get reflected to 8, 7, 6, 5. Okay, so you want to reflect from right to left, or right to or left to right, however you want to look at it, but basically in the horizontal direction. That's how you want to reflect it. Okay, so let's see. Okay, yeah, so sepia test cases pass, as you can see here. So next one we have to code is the reflect function. So let's go ahead and do that. Okay, so one thing to keep in mind is that reflect and blur functions will be modifying the actual pixels, right? So what we want to do is we don't want to do it in place, meaning we don't want to modify as we go along, because we may sort of corrupt these values, or or the final result might change, right? Meaning that, for instance, like later on when we talk about the blur algorithm, say we take a pixel and look at the 9 squares around it, we still want to retain the values of the original matrix and apply it to each individual pixel, right? While we are iterating, if we sort of change the matrix itself, that's not what that's not intended, that's not what we actually want. So I'll repeat that again because I know it can make it look confusing. So while we're iterating through matrix, we actually don't want to modify the pixels in place, because subsequent pixels might read that value and it will be wrong because it'll be the modified value. The thing that we actually want is we want to apply the transformation for each individual pixel from the original pixels around them, okay? So if you didn't quite catch that, just rewind and just know that you have to use a temporary two-dimensional a temporary image and write all the changes to that, and in the very end copy it. Because if you modify in place as in as you go along the loop, if you change the pixels, other pixels around it will read the modified value, where in reality what you actually want is for other pixels to read the original pixels in the image, okay? So that's the key to the problem. So let's code reflection with the temporary buffer. All right, so I'm going to, I need to have a temporary buffer here. So I'll say RGB triple temp. I'll declare the same dimensions as with height and width here. And what I'll do is I'll do my transformations to temp, and then copy it finally. Copy to final image. Okay, how do I copy to final image? That's pretty straightforward. Since it's the same dimensions, I just have the standard loop here. I just copy the standard loop, boom, and I just say temp, image at ij is equal to temp at ij, okay? And similarly, so that's the copying part here. And I have to do the same thing with blur also. We'll get to that, but I'm just gonna paste the code here for temp. And the reason again is that we don't want to modify those pixels in place because other pixels will read modified values. We want to do it to a temporary image and then copy it over, okay? And read the original values as we go along, okay? So what we're going to do here is something like this. So imagine that if you have a matrix like this, 4, 3, 2, 1, you know, 1, 2, 3, 1, 2, 3, 4, and then, 4, 5, 6, 8, or something like that, right? How would you reflect this? Okay, so that's the question we have to ask. So what you would do is normally you would, to iterate over this two-dimensional array, you would have the standard for loop like this, right? You would have this sort of standard nested loops, okay? But the standard nested loops, what we do is, like, if you have something like this, I equals 0 and I is less than height, and j is equal to 0, j is less than width, it goes each row in this order, like here, like here, like here, like here, right? So it starts from 0, 1, 2, 3, 0, 1, 2, 3, okay? So, but we don't want to actually do that. We want to actually read from the end. We want to start at the end of each row, and we want to read it in reverse. So that is the key here. That's how we essentially reflect it. We start from the end, and we read it in reverse, okay? How might we do that? That's pretty straightforward. So what we do is, instead of j equals 0 and j less than with j plus plus, we'll say it's equal to the width minus 1, because that's the last pixel. In this case, it would be 4. J is greater than or equal to 0, because we want to terminate when we reach 0, j minus minus. So that's how we're reading from the last one for each row, okay? And what we do is we write it to a new temporary, we write it to the rows of our new temporary image here, okay? So what we do is, initially we have some variable called maybe current position set to 0, okay? So what we say is current position plus plus on each iteration. So current position is 0, so you have these 4 spaces here. So current position is actually 0 in a new temporary image. So what we're going to do is going to write to 0 here from 4, okay? So it's going to put 4 here. So in the next iteration, it's going to decrement this original row because we're reading from reverse, and it's going to increment our current position here, okay? So it's going to be 3, and we're going to decrement here, which is j minus minus, and we're going to increment current position. So now it's going to put it at 2, and then decrement, and then increment. Okay, so now, as you notice, we reversed each row completely. So that's how we go about it, okay? So let me just code that up. So I have current position equals 0, and I increment this. On the other hand, I decrement j, and j would be corresponding to the pointers of this here. So this would be j. J would start here. Current position would start here for this new guy right here. It would be, temp would be empty initially, and then you would put here, okay? So let me go ahead and do that. So what I'm going to do is something like this. I'm going to say temp at current position, right? Because we want to write here, is equal to image at and current position. And what I want to do is we'll figure out the row later, but I comma j, okay? And I believe it should be the same row actually. Yeah, it should be the same row. So current position. So this should also be same row, which is in this case it be the 0th row. Okay, we're just reversing each row. Okay, and yeah, so we go ahead and just copy over the reflected values to a temporary buffer here, and in the end we just assign it to the original matrix. So let's see if that works. So hopefully that made some sort of sense. Let me go ahead and make filter and run the reflection of the yard. Yeah, reflect. Okay, so yard originally has this person coming from the right to the left. He's going towards this direction. So if you reflect it, it should be he's coming from here and he should go this way. Reload. Okay, there we go. Okay, so we've successfully reflected it. Let's run the test cases and see if it passes. While that's running, let me just quickly introduce to the next prompt, okay, which is blurring, okay? So we talked about the idea of transformations earlier in sepia. Now the current transformation we have to apply to each pixel is to look at its neighbors, the 9 neighboring cells, and we want to sort of blur them out, okay? And the way we blur them out is we count the total number of squares and then take the average of them, okay? So the algorithm is called as box blur, so let's look at that. But even before that, let's see if it worked. Okay, so reflect cases now all passed. Okay, so now let's work on blur. Okay, so the algorithm that uses box blur, and we can actually, when I was researching this, it was really useful to look at some box blur algorithms online. I think there was one really good blog. I think that it was this one, which had a really clean algorithm here, which is this guy right here. It's very easy to implement. So let me just copy this. So this is in English-like language, what we do, and then I'll just implement that in code, okay? So let me go back here. So we have to look at its 9 neighboring cells around them. So as you can already see, I've created this temporary image, and I've also created this copying to the final image. So let me go ahead now and copy here. Okay, so now I'll paste the algorithm. So this is the algorithm, right? For each row and for each column. How do we do that? That's standard for loop here, right? What do I have to do now? So I have to count the neighboring cells within one radius, okay? So what I mean by that is, say I loop over, say I'm at 6. I have to count a radius of 1 from every, from the 6th pixel and 1 radius outward. So that would be 1, 2, 3, 5, 7, 9, 10, 11. Similarly, if I'm at 11, 10, 14, 15, 16, etc. But if I'm at the corner pixels, for instance, if I'm at 16, only 12, 11, 15 will be counted. Okay, so that's the general idea of it. If you're confused about this, watch the walkthrough, please. So how do I do this? So for every neighboring cell within the radius of one direction, add the color to the total. Okay, so what I'm going to do is, and the final color will be equal to total divided by count. Okay, so I have to each, as with sepia and grayscale and everything, I have to take each individual pixel along the green axis, the red axis, as well as the blue axis, okay? So what I'm going to do here is I am going to set the count to 0, okay? So I'm going to set the int count red, count green, and then actually I don't need to have individual counts. I guess we can just have count 1, okay? And then what I do is for every neighboring pixel within radius of 1. Okay, so how do I do that? In order to do that, what we have to do is we have to look at all the 9 neighboring cells. Okay, so what I'm going to do, there's multiple ways to do this. You can add offsets, but the way I like to do it is I like to just initialize an array of coordinates. Okay, so I'm going to say int x coordinates equals row minus 1. Row and then row plus 1. So this is along the y-axis, and the y coordinates will be actually, so I'll just say row coordinates because I don't want to get into y or x. So I'll just say row coordinates and then column coordinates, like so, okay? It will be column -1, column +1, okay? Now what I'm going to do is I'm going to take all the possible combinations with this. So it's going to be row -1, column -1, row -1, column, row -1, column +1. And the next iteration should be row, column -1, row, column, and then row, column +1. So basically I generate 9 different coordinates like this, okay? How do I do that? I just use a standard nested for loop. So I'll call this R0, R is less than 3, R++. For int C is equal to 0, C is less than 3, C++, okay? Okay, so C++, whoever gets the joke here, okay? Okay, so what we're going to do now is so my current coordinate is actually row -1, column -1, right? So I can get the current row equals row coordinates at R, and my current column is equal to row coordinates at C, okay? So now what I have to do is I have to validate whether they're in bounds, okay? So I'll repeat what this step is doing. So this step is just looking at the 9 neighboring cells around them. I generate the coordinates, and what I do is I just have to validate that it's within bounds, right? So if current row is greater than or equal to 0 and the current row is less than the total height, right? So in this case it would be height, and the current column is greater than or equal to 0 and current column is less than or equal, less than the width, right? Then what should I do in this case, okay? So in this case, what we should be doing is it's a valid coordinate. So what I have to do is I have to add them up and take the average, okay? So I want to do count plus first, and then I have to add the color to the total, okay? So I'll have total, I'll create a total here. So float, total red, total green, total blue is equal to 0, okay? And here what I can do is I can say total R is equal to the current pixel, right? So RGBT triple pixel equals the current pixel. So this will be image at current row and then current column. So I'm looking at a valid pixel here. So now what I do is I just take the R value from here. So pixel dot, I actually need to add it to the total, right? So I do total R plus equals pixel dot RGBT red, right? So I go back here and I say all these stuff here. So these entire pieces here, I have to do this entire thing, right? So I have to add them into the total, right? So let me go ahead and copy paste that. So this will be pixel, image ij.rgbtq. You can also do pixel. You can initialize in a temporary variable and do that. And then total green is equals this guy right here, and then total blue plus equals this guy right here, okay? So now I have the totals. So now all I have to do now is after I grab the totals, okay, the final colors will be equal to the average depending on what the count is. So it's like a weighted, almost like a weighted average kind of deal, meaning that it's dependent on the count. So let me go back here and try to put my parentheses there. Okay, so now I have examined all the directions around the neighboring cells, all the neighboring pixels, and I have also validated the pixel right here. Okay, so now what I have to do is I have to just assign it to my temporary buffer here, because as I talked earlier, we don't want to change the original matrix yet, because other pixels might read the modified values, which we don't want. So temp at what we'll say is temp at ij is equal to temp at ij dot RGBT red. So let me copy this. Yeah, is equal to the total R divided by count, and I have to round that up. So let me do round of count, and then round of total G divided by count, and then the round of total blue divided by count. Okay, so now I've taken the count and initialized my final color, and I just set the pixel. That's what I exactly did right here. Okay, so now all I have to do is assign it back to my original image, and I claim I'm done. Okay, so a little more involved and complicated, but hopefully not too crazy. All I have to do is I have to iterate through my two-dimensional image, and for each pixel I look at its neighbors, which in this case I've formed a piece of coordinates, a pair of an array of coordinates, and I look at the coordinates and I validate each one whether it's in bounds. If it's within the bounds, I dereference and I take the pixel at that given location, and I add the R value, G value, B value, and I increment count, and at the end I assign it back here. Okay, so now let's go ahead and test it. This should be hopefully compiling, but let's check. Okay, make filter. Okay, we have tons of errors. Float. Oh, I don't think I can do this. Can I? I don't know. Maybe I'll try this. Yeah. How about that? Okay. So we have unidentified use of row. Okay, so let me check it here. Row -1. Oh, okay, I see. So let me call this row instead of I. Let me call this column instead of J. And this will work. And then row, column. Let me see here. Row coordinates, pixel, sorry. Yeah, this should be pixel also, actually. So pixel at that, okay. And yeah, so let's, this should be row column as well. Row, 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 okay. And this J will be column here, okay. Column, okay. So, so yeah, so now let's check. Okay, brackets are not allowed here. To declare an array, place brackets after the identifier. Probably it's a syntax thing, I think. Yeah, in Java, I think the brackets are like that. I don't remember actually. Let me check. Okay, maybe it worked. So now what I have to do is pretty much do the filter, but I am actually running, in this case, I am actually running the blur, right? So I changed to a B, I believe. Okay, so now let's check the out, I guess. Okay, that's clearly wrong. So let's, so it's all black here. So we clearly made a mistake somewhere. So let's go back and check where we made a mistake. And let me refer to this. 6 values. Okay, so let's give me a minute here and I'll try to see where the problem is. Okay guys, welcome back. So I think I found the bug. The bug was basically, I was doing image at row column. This is exactly what I told not to do. If you do this, then it'll modify the buffer in place, which we don't want. This should actually be temp. Okay. So this should be actually temp because it'll modify to a temporary buffer and write to a temporary buffer. And the original pixels still keep intact. And current row equals this. So one more thing, I think this should be column coordinates. Okay, so let's, I think that's pretty much it. So let's go ahead and make it and apply the filter algorithm on, say, tower, right? Reload. Okay, that's better. Okay, so now it's clearly blurred. Okay, so now we actually see the bug was this should be column coordinates and then you should write it to a tab. Okay, now let's try submitting it. Okay, great. It passes all the tests. So now actually let's submit it using CS50. Submit. So I'll explain at a high level again, summarize what we did here. So for the grayscale, we have to just take the average of the pixels and write it to the original image here. For the sepia, we just apply this transformation, which is like a transform values mathematical formula, and we assign it here, and if it's greater than 255, we cap it. For reflects, it's also a little tricky. We have to just reflect it, but we have to make sure that the original image still stays intact. So we write it to a temporary buffer here, and we loop through each row in reverse and write it, and then write back to the original image. With blur, also the idea is we have the temporary buffer. We apply the algorithm in which we look at all the neighboring cells and we validate them. That's the important part here. And we add them up and we just divide it by total count of the neighboring valid cells, okay? And once we divide that, we just assign it back to the red, green, blue values correspondingly for that particular pixel. And that's why we use this temporary buffer here. So in the end, you have this temporary buffer or temporary image, which has all the modified values for the blurred image, and we just write it back to the original image, okay? So now let's go back here and then see what we got. Okay, 22 out of 22, that looks good. Style is questionable, but you know, hey, I'll take that, okay? So in the next program, it's filter more. So let's take a look at that also. Problem set, we're going to focus on filter more. So with filter more, we want to more or less apply the same effects as filter less, but there's one additional effect that we want to apply, which is the edge detection algorithm. And the edge detection algorithm, I believe it's called some Sobel operator algorithm. So we'll take a look at that. So let's go ahead and get started. So we'll do get filter zip. So let's go ahead and do that, and we'll unzip filter.zip and we'll delete filter.zip. Okay, so that's done. So let's go now inside okay, clear. So now let's go inside filter here. So in filter, we have to do the same exact idea. So if I open filter here, we have helpers.c. Let's open that. It has the same exact functions as grayscale, reflect, and blur. So let's copy that. So we don't have to do the same thing again and again. It's the same exact thing. So we can just copy that. Helpers. There's no sepia. There's reflect. So we're going to take reflect, copy that. Reflect, copy that. And then blur, we're going to copy that. Okay, and we can delete this algorithm. Actually, let's copy this and delete. So take this and paste this, and we're going to delete this. Okay, so now we have actually this is edges, sorry. Let's take this and, okay, and this is our edges, okay? So now let's make sure that our test pass by running check50 and make sure that whatever we have already doesn't fail. So let's go ahead and do that. While it's waiting for that, okay, so blur works, edge detection doesn't work yet, okay, because we haven't coded that. So let's go ahead and code that. So the way it works is that we have to apply this matrix, which there's gx and gy, and we just have to apply it to the 9 pixels around that, depending on which one is inbounds. So the idea is that we first have to create this matrix. So even before we do that, let's go ahead and actually create it. So where's my helpers? Okay, not this one. This one is the one. Okay, as you can see here, the test for blur passed, but the test for edges failed because we haven't coded edge detection yet. So let's go ahead and code it. Okay, so I'm going to open helpers.c, and the algorithm we want to apply is edge detection. Similar to blur, we're going to be creating a temp image here. So let me just copy that, and after in the final thing, I have to just copy over to the final image. So I'm going to have these same steps. Now I'm going to apply the algorithm, edge detection algorithm. So according to this wiki here, the way I do that is I create these 2 matrices called gx and gy, which is a 3 by 3 kernel matrix. So I just go ahead and initialize them. So what I'll do is I'll say int gx 3 by 3 is equal to like that, okay. Let me just look it up. Initializing two-dimensional matrix in C. Okay, so yeah, I can do something like so, right? So gx equals 3 by 3, and I'll go ahead and I initialize it with these things, 1 0 negative 1. So gx will be 1 0 negative 1, 2 0 negative 2, 2 0 negative 2, and finally 1 0 negative 1, 1 0 negative 1. That's going to be my gx operator. The gy matrix is going to be 1 2 1 0 0, 1 2 1 0 0, and then negative 1 negative 2 negative 1. So I put negative 2 negative 1 negative 2 negative 1, negative 1 negative 2 negative 1. Okay, so that's my two matrices. Let me just make sure those are the right ones. So negative 1 0 1 2 0 negative 2 0 2, negative 2 0 2, negative 2 0 2, like so. Oh, I think it's the other way around, sorry. Negative 1 0 1, negative 2 0 2, negative 1 negative 1 0 1. Okay, and gy is going to be negative 1 negative 1 negative 2 negative 1, negative 1 negative 2 negative 1, and then 0 0 0, and then 1 2 1. So I'm going to move this here. Okay, so I think that those are my matrices. Okay, so let me double check them again. We have the right matrix. Yep. Okay, so the next step is, once I have this matrix, I have to do the same exact idea as blur, but I have to just apply a different algorithm or transformation. So I go through my row and column here. So I'm gonna do this, and what I do here is I actually have to basically compute while it's a valid neighboring cell. I have to apply it on the red, the green, and the blue values, right? So what I'm going to do is I'm going to take this helpers here. I'm going to apply the same algorithm here. So I'm going to have row this exact logic here too. So I'm going to use row coordinates and column coordinates, right? So row is row minus 1, row plus 1, column minus 1, column plus 1. And I'm going to do this validation. So while it's a valid cell, what I have to do now is I have to do gx times so what I have to do is I have to have the red gx, blue gx, and green gx. So let me go ahead and initialize them. So insert total r, red, I'll call it gx red, gx blue, and then actually gx green, and then gx blue. Okay, so here what I'm going to do is I'm going to apply that transformation, right? So what I'm going to do is I'm going to say gx okay, so what I'm going to do is I'm going to say I'm going to get the current pixel here, which is this line. Okay, and now what I'm going to do is instead of doing this, right, so pixel dot red, pixel dot blue, etc., what I'm going to do is I'm going to say the gx red plus GX green, GX blue, okay, equals the GX at row column times pixel at this thing, right? And then do the same thing here, GX at row column times this guy, and then do the same thing with GY. GY at red equals this. Okay. Okay, so now what I've done is essentially I've multiplied each given pixel by the corresponding value in the matrix, and once I've done that, in the very end I have the totals for GX red and GY red. So let me go ahead and do that also. Instead of GX here, I also have to GY red, GY green, and then GY blue. So now what I have to do is outside here, after I compute my given algorithm, right, now apply the square root function to the GX and GY. Okay, so what I say now is something like int final red is equal to make sure I imported math, include math.h. Okay, so what I do is I say square root of GX red times GX red plus GY red times GY red. Okay, so this is that formula that I'm applying here. Okay, so if I go back here, what I have to do here is I have to apply G equals GX squared plus GY squared, right? That's exactly what I'm doing here. So but you have to do them along each individual coordinate here. So square root of GX GX red times GX red is GX red squared plus GY red squared, right? And square root turns like a float, so I cast it into a integer using round. Okay, and I have to do this along each individual dimension. So red, green, blue, right? And then this will be green, 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 and then blue will be GX blue squared, right? GX blue squared plus GY blue squared. Okay. So GX squared plus GY squared, GX squared green plus GY squared green, GX blue squared plus GY blue squared. So this will be blue, but you have to make sure that it's within the valid bounds. So it might exceed 255, in which we have to cap it. Same exact idea as sepia. So what we're going to do now is we're going to say temp at row column. I think I had those lines here, this one. Okay, so now what we're going to do is we're going to say temp at row column RGBT red equals final red is it greater than 255? If so, then cap it at 255, else take final red. Okay, similarly, if final green is greater than 255, then cap it at 255, else take final green. Similarly, if the blue is final blue is greater than 255, cap it at 255, else take final blue. Okay, so what we can do now is that's pretty much it. So I declare all my matrices here, and I apply the transformation using the algorithm that was proposed. Okay, and I think that's pretty much it. Let's unless I see any typo, let's go ahead and test it out. This should be okay. I think these are right. Okay, so let's go ahead and test it out real quick and just make sure first it compiles. Okay, so let's go here, clear, make filter. Okay, so that works. And to run this particular operation, what we want to do is filter E, right? So I want to filter E, and let's check. Filter E. Okay, so let's check out. Okay, so that looks fine. So let's go ahead and actually try submitting it, or running through the checker first. Okay, so I'll repeat what I did here. If you were not able to follow this, I suggest you to watch the walkthrough. So basically the idea is that I declare my two matrices here, which is gx and gy, and I have to do the same exact idea as blur, but instead of adding each individual pixel and dividing by count, what I have to do is I have to use some matrix and do some matrix multiplication, and in the very end I have to just take the square root of the gx squared plus gy squared, and if it's greater than 255 I have to just cap it. Okay, so let's go ahead and see what we got. Okay, so it passes all the tests, so now let's try submitting it. So this is filter more, so let me go ahead and submit. Okay, so that's pretty much the underlying idea behind it. Hopefully it's not too complicated, because it's borrowing most of its logic from the blur function, but instead of this algorithm here, only these lines change. Lines total R, total G, total B, and then instead of doing this, you apply the square root function, and in place of here you would apply the matrix multiplication transformation. Okay, so that is the only difference. Let's check what we got here. So yes, I want to submit it. So yeah, that's pretty much it. So let's go ahead and see what we get. Okay, open this. Okay, it's waiting on results. Let's wait on it. So yeah, that was the edges, and like I said, I encourage you to read the walkthrough and read the specification one more time, because they provide most of the information here. But yeah, so okay, 23 out of 23, that's good. Okay, so now after this, I believe after filter, I believe the next programming prompt is the recover. So let's take a look at that. Okay, so the final problem is recover, and in recover the idea is that we're given a raw image file, and we have to recover the different or various images from them. And yeah, that's just the basic idea. And the way they're structured is that this raw file has some blocks, what is known as some blocks, and this block is sort of a logical entity that exists in memory, and we have to read through the blocks and just write to the images accordingly. Okay, so that's just at a high level, that's just an idea. So let's get started here. And yeah, so I have my recover program here. I change into I already changed directory, so I'll just do this. I need to get recover.zip, and I need to unzip recover.zip, and I need to delete recover.zip after that. Okay, so now I have recover, so let me go here, clear it out. Okay, so now car.raw, which is the raw file that is given to us, and we have recover.c, which is the file that we're supposed to fill it in. Okay, so this is a template that looks like this. So what we're supposed to do now is implement the recover algorithm. Initially, what we'll do is they say that we have to throw an error in case where they don't specify any arguments, right? So let's do that real quick. So that's the easier part here. So if argc is not equal to 2, then we return 1 saying that some error occurred, along with printf, and we print the message there. So we print usage recover image. So it's saying that you have to supply one argument of image, okay? Else, then we know it's, then we also try to open it, and if there's an error, we print that there was an error, right? Somewhere it says here, or I can't remember if they do it in the walkthrough, but let's try to open it like so, and we'll just say image, or actually this is the raw file, right? Raw file, we'll call it file, just follow this, and if file equals null, then there was some error occurred, right? So we just print f, you know, error occurred, opening a file, right? Opening the raw file, and then we return 1. Okay, so these are our error conditions. So now we can now we have a valid file to read. Okay, and we can start reading the different images now. So how might we do that? Okay, actually this problem is straightforward if you just follow the algorithm that is given by Brian. So I highly suggest you to just look at the pseudocode here and translate that into code. Okay, so what I'm going to do now is I'm going to take each line individually and what the video says, and I'm just going to put these as comments in my code. Okay, and all I have to do is just translate from English to code. Yeah, for this particular problem especially, they give you 90% of solution. Pretty much this is the solution here. So all you have to do is just take this and just follow it and write in code. So what I'm going to do is I'm going to take this and start typing all these comments out, and I will get back to you after I finish typing all these pseudocode in comments. I have translated and written everything the pseudocode has, along with some additional stuff they have said in the video here. So all we have to do now is just translate these English-like statements into code, and we should be good to go. Okay, so now let's get started with this. So now we have to open the memory card first, okay, and start reading it, right? And you have to repeat until the end of card. Okay, so what I'm going to do now is for these two statements here, I have to keep on reading until the end of the card, right? So what I'm going to do right now is I'm going to keep on reading it while true, and then inside here I'm going to break anytime the condition is false. Okay, so what I'll do here is I'll say while true, repeat until the end of card, right? So I read 512 bytes into the buffer. Okay, so while true, I'll put the ending comment here, return 0 here, it's successful. Okay, so repeat until the end of card. Okay, how do I do that? I want to first use fread function to read 512s into buffer. So let me go ahead and initialize a buffer structure. So what type should the buffer structure be? Okay, the prompt says to make it easier, you have to read bytes, so you can just declare this as a type def. So let me declare this, and let me declare some more variables here. This is standard int.h, so I have to import that. So include standard int.h. Okay, and now we have to import a buffer, if declare buffer structure. So I'm going to say byte buffer, and what size should this be? This should be, we're reading in 512 chunks, I believe. So 512 blocks. So each block is 512 bytes. So what we'll do is we'll say define block size to be equal to 512, and that's the size that we should be reading. So 512. Okay. So now these are my structures, so I can go ahead and read it from here. Okay. So what I'll do is I'll say fread buffer, because that's what I'm reading into. And what is the size of each individual data type? That's just the size of my byte here, right? That's the size of each element inside my buffer. And what are the other arguments to fread? I can take a look at that. So let me just look that up real quick here. So fread, the count, right? Saying how many recent array of count, right? So it should be the block size here. So I want to read block size number of elements here. And finally, the final argument is the stream itself, to what I should actually read from. So in this case, I want to start reading from my file, right? My original file, okay? And if you notice here, this actually returns a size t, which is a positive integer, right? Of the total amounts of bytes that is read, okay? What to remember here is that if the size or count is 0, the function returns 0, and then like it's the end of the file pretty much. So if the count is 0, it's the end of the file. So what I'm going to go ahead and do right now is initialize size t bytes read, and I am going to say bytes read equals fread of that, right? And if bytes read is equal to 0, that means it's end of that means break, it's the end of file, right? So what this essentially means is that, say you have blocks, right? So as an example here, so say I have block 1, actually, yeah, let's say block 1, block 2, block 3, and block 4. And say this block 2 is a JPEG one. That's where JPEG starts. So after it reads here and say block 4 is less than 512 bytes, after it reads this and it reaches the very end, what's going to happen is that you'll have to, so after it reads the entire block, it will be a non-zero integer, so you read that, and in the next iteration you'll try to read past the block. There's no blocks left, so this will return 0, so that's why it's going to break out of this loop here. Okay, so so here's, it represents the bytes read. Okay, so if it's end of file, I break it, else I continue reading it, right? So in the next scenario, what I have to do is I have to say if it could be a start of a new block, right? So if a start of a new JPEG, how do we determine if it's start of a new JPEG? We do the condition that's specified in the prompt. We say, I don't know if it's here on the notes. Let me take a look. So here we do this condition of, where was it again? No, not here. It was in the notes, I would believe. So in the notes, I go to the notes here and it said start of JPEG or something like that. Here, this one. So I read it, right? And once I read it, I check whether it's a start of a file. So like so, if the byte, if the buffer at 0 equals that, if buffer at 1 equals that, if buffer at 2 is equal to that. And in the walkthrough, it also specifies that you have to have another condition here, which is to say that somewhere here, I forget where. Let me just quickly here. So we have to use this. So buffer at 3, right? And buffer at 3, and 0xf0 and 0xf0. 0xf0 is equal to the let me go back here, is equal to 0xe0, is equal to 0xe0. Okay, so if that is the case, it's a start of a new JPEG, else it is not the start of a new JPEG. Okay, so if it's a first JPEG, so we have to put all this stuff inside here, else it is not a new JPEG, and keep writing to it. Okay, so what do I have to do? If it's a first JPEG, mark as a first JPEG. Okay, how to determine if it's a first JPEG? We have to have some sort of Boolean variable. Okay, so I'm going to go ahead and declare here Boolean is first JPEG equals false. Okay, and Boolean first JPEG equals false. And then what I do here is, if it's a first JPEG, if is not a first JPEG, I mark it as a first JPEG. Okay, so is first JPEG equals true. Okay, so then what I do is I say else, close the current file that it's being written to. Okay, and open a new file. Okay, so if it's not a first JPEG, I mark it as a first JPEG, else I have to close my current file being written to. So I say fclose my current file that I'm writing to, right? So I'll say current file, and what I'll do here is declare another structure called current file being written to. So I have to close my current file being written to and open a new file. Okay, so what I'm going to do is I'm going to open a new file. So I'm going to do f open, and I'm going to have a current file name, the new one, like 0000001, etc. So my current file name is going to be another structure here. So I'm going to declare that also. Char current file name is maybe 100 in length, right? So what I'm going to do is I'm going to open current file name for reading. Okay, sorry, for writing, and I'm going to assign that to my current file. Okay, so that's that. So and then I have to write the bytes I've read so far, right? So what do I do here? So I basically the next step is pretty much I have to I created my current file name, right? So I have to go ahead and say what type it is. So this is going to be printf current file name, and this should be the format in which it's specified. So I think here it says something about like this, right? So sprintf file name percentage 03i JPEG, and then the number here. So I'm going to do the same exact thing. So current file name, and then I'm going to say percentage 0.3i dot JPEG, and I am going to specify the current file number. Okay. The current file number is going to be integer, which I have to initialize. It's going to be 0 initially, and once I write to it, and if it's a start new JPEG, I increment it. So I say current file number plus. Okay, so that is my new current file, and I start I open it, and then in the later iterations, it's going to start writing to it. So else, if it's already found a new JPEG, how can we already say if it's found a new JPEG? That's straightforward. So we have some sort of Boolean variable that says if it's already found a new JPEG, and start writing to it, right? So let me go ahead and do that. So Boolean found JPEG. Okay, found JPEG equals false. So all I have to do now here is say if found JPEG, then keep writing to it, right? So if it's found, then what I do is use fwrite again, and I have to write that much amount of bytes to it. Okay, so how much am I going to write here? So what are the parameters for fwrite? Let me take a look here. So fwrite, there's the buffer that I'm writing to, and size, count, and stream. Okay, so what I'll do is I'll say same exact parameters almost: buffer, size of byte, block size, and end file, right? Basically, actually, instead of block size, I'll say amount of bytes read. Okay, amount of bytes read. So I'm writing to that, and I'm writing to my current file. Okay, that I am examining. Okay, and after I do that, right, so let's quickly run through some iterations. Okay, say I have 4 blocks. Okay, what it's going to do is say, okay, I'm going to start from block 1. I'm going to read 512 bytes. Okay, so in this line statement, in this statement here, it read the 512 bytes. It's not equal to 0. It's not end of the file. So it's going to say if it's a start of new JPEG. So it's not a start of a new JPEG. So it's going to go here. Okay, and say else if it's found a new JPEG, and in this case found JPEG is set to false because it's not yet initialized yet. In that case, I'm going to start writing. It's not initialized yet, so it's not going to enter here. So what it's going to do is it's going to skip that particular block. So this block is skipped. In the next iteration, it's going to come back to the top of the loop here again, and it's going to start from B2. Now B2 is a valid block. It's going to read this 512 bytes. And it's going to say if it's the start of a new JPEG, in which case it's true. If it is the first JPEG, then mark it as the first JPEG. So yeah, it is marked as the first JPEG. We don't have any previous blocks that we have seen that we're writing towards. So yeah, so it just goes to if else isn't executed, and it increments the file number. And one thing we also have to do here is we also want to say that we want to also write it, right? So we want to do fwrite the first block, right? So we want to do buffer, same exact statement as this one, right? Bytes to the current file, and the current file in this case would be with 0. Okay, so we can actually move these statements outside here. So what we're going to do is we're going to do something like this. Okay, like that. Okay, so what we're going to do is yeah, like that. Okay, so now what's gonna, so to repeat that, right? So block 1 was not a valid block. It didn't enter this if, it entered this else, but there was found JPEG was set to false, right? So it didn't go there. Okay, on the next iteration, it goes to block 2. Block 2 is actually start of a new JPEG, so this clause is true, and then found JPEG should be marked to true, saying that it found a valid JPEG. And then if it's a first JPEG, which is the case, because if it's not a first JPEG, then I mark it as true, so it enters this if here, right? So it's not seen previous JPEGs, in other words. Then I initialize my current file name, which is currently file number is set to 0, so I initialize to 0, and this is going to be 0.jpg, the current file name, and I open that for writing purposes, and I write how much bytes I've read, okay? And I increment file number. So now file number will be 1, okay? So now I have sort of written and opened and written to my file 0 the amount of bytes I have read, okay? So in the next iteration, what will happen is that block 3 is also the JPEG that I previously saw. So it's not a start of a new JPEG. On the other hand, it goes as else. The if found JPEG is true, so I write how much bytes I've read, okay? So in the next iteration, I go to B4, and B4 say it's the final end of the JPEG file. So it's this is false, and it's going to say, okay, I already saw a previous JPEG, I'm going to write to it, okay? So that's fine. What about, so actually, so say this was only structure here, and this was less than 512 bytes, so it writes here. So after this next iteration, it's past the end of the file, so bytes read is equal to 0, right? So it's going to break out of this while loop. So what I'm going to do outside here is I'm going to, so once it breaks here, then I'm good to go. I just have to close all my files. So I'm going to close my image file, the original image file, which I read, which is the raw file, which is file here. And I'm also going to close my current file that I was reading, current file. Yeah, that's pretty much it. So let's run through another example here. So say this was the end of the JPEG file, and then a new JPEG file starts here. So say it's B5, and then B6 is the end of this JPEG file, right? End of this JPEG file. So in this case, what do we do? So let me run through it again. So we started block 1. Block 1 is, it enters this while loop here. It reads 512 bytes. It's not a start of a new JPEG, so it's going to go to this else clause. This flag is not set, so it's going to go back in the beginning of the loop. So it's going to skip this block. In the next iteration, block 2 is an actual start of a valid JPEG block. So it's going to go here. It's going to say this is, it's going to check whether it's a valid JPEG block, in which case it is. So it's going to mark a found JPEG as true. And it is an actual first JPEG file, so it's going to mark that as true. There's no previous JPEGs that were found. And it's going to it's going to create the string 000.jpg, right? And it's going to open it for writing, okay? And it's going to write the initial bytes that it read from here, okay? So after it does that, it's going to increment the file number, in which case it's going to be 1. So at this point in time, it would have actually read the JPEG. So B2 would be created, opened for writing purposes, and it would write the initial bytes. In the next iteration, it's going to go to B3, okay? It's going to go to B3, and it's not a start from JPEG, but it's the continuation of a previous JPEG. So it's going to go to this else clause. This found JPEG is already set, so it's going to continue writing the B3 the bytes that it read in this line here. Then it's going to go to the B4. It's the end of new JPEG. It's going to read the bytes. It's not going to enter here. It's going to go here. Found JPEG was already set to true, so it's going to write these contents here, okay, to the B4, okay. Now here's where it gets interesting. So say B5 is the start of a new JPEG. So this is start. B5 is the start of a JPEG, and what it will do now is we'll go back to the loop. We'll read 512 bytes. And if it's start of a JPEG, which it is, it's going to set the found JPEG as true. And now here is false because this was only set one time. So there, in this case, there are previous written blocks. So it's going to close the current file. Current file here will be 000.jpg, right? So this was the previous file was 00.jpg. So it will close the previous file, and it will create a new file with the string 001.jpg, and it will open that for writing, and it will write the bytes that read, and then file number will be 2, okay? And then in the next iteration, it will start with B6. B6 is not a start of a JPEG file, but it is a part of the JPEG file, so the found JPEG is set to true, so it will write the amount of bytes read to the current file, okay? And after that, it's going to go past the block size, so it's going to be end here. So it's going to read past the end, so the bytes read will be 0, and it'll be the end of file. So it's going to break out of this loop because I put a break here. Okay. So after that, it breaks out of the loop, and I just close my raw file, and I close my current file. So my current file in this case will be the last file written to, which was 001.jpg. So it will close it. Okay. So this algorithm sounds good because I've run through it and I've seen the states, but let's actually check what actually is if it compiles and if it runs. Okay, so I'm gonna do make recover, or actually, sorry, it should be make or sorry, yeah, it's make recover. Sorry. So I get a bunch of error messages. So let's examine undeclared bool. Okay, so in boolean, I believe I need standard bool. So let's take care of that. Standard bool dot h. Okay, so that's that. Okay, so let me just clear it and then recompile it. Okay, so now we have some other error messages. So let's go through this. Current file, did you mean current file? Okay, so we misspelled some names, so let's take care of that. So let's do current file like so. So that's current file, clear, and then make it. Okay, so current file name, file number. Okay, so I guess we made some more mistakes here. Current file name is actually a file name. Let me do current file name. Okay, file name is actually a string, basically char buffer here. So file name, okay. So yeah, so that's that, and let's make it again. So let's clear it and then make recover dot c. Okay, now it works. So let's do recover, and then let's pass in raw card.raw. Okay, so we got some images here, as you can see. Let's see if it's a valid one. Okay, so it works. Okay, so I'm able to recover all the images, as you can see here. So this is fine. Now let me close this, go back here. Let me run a checker on this and see if it passes everything. Okay, so remember that basically I just took the pseudocode from what the walkthrough gave me, and I created my own example here, and I just ran through the code I wrote to make sure that it follows whatever, you know. And if there are any, if the logic breaks, I add in extra variables, extra conditions to make sure my logic works. Okay, so that's how we should typically do it. Draw some diagrams out, run through your code, and see if it works. And if it works, then try running the checker. But if it doesn't work, you have to figure out why it doesn't work. Okay, for that, I would suggest forming some examples of your own and see, like, the way I started was I just started with simplest examples in which it had block 1, block 2, block 3, block 4. And after that, I sort of added additional blocks, and I ran through my code to make sure it functions as expected. So let's try submitting it now. And yeah, let's open this and see if it successfully works. 6 out of 6. Okay, so we successfully finished the problem recover. If there are any questions on the recover program or any of the programs I discussed previously, like filter, please leave it in the comments below. Hope this helped. Good luck, stay safe, and have fun coding.